In 2017, Oumuamua became the first confirmed interstellar visitor to our solar system, sparking debates about its true nature. Now, with the recent discovery of 3I-ATLAS in 2025, scientists are comparing these mysterious objects and finding that Oumuamua's bizarre properties look increasingly artificial. While most interstellar objects behave predictably, Oumuamua's strange acceleration, unusual shape and reflective surface continue to defy explanation. The more we learn about typical interstellar objects, the more Oumuamua stands out as something potentially extraordinary and possibly not natural at all. The discovery of 3I-ATLAS. The discovery of 3I-ATLAS in January 2025 by the Asteroid Terrestrial Impact Last Alert System marked humanity's third confirmed interstellar visitor. Unlike its predecessors, 3I-ATLAS immediately displayed characteristics that astronomers expected from natural interstellar objects. Dr. Robert Warwick, who also discovered Oumuamua, led the initial observations that confirmed the object's hyperbolic trajectory and interstellar origin. 3I-ATLAS measures approximately 200 meters in diameter and exhibits a normal comet-like behavior with visible outgassing as it approaches the Sun. The object's spectroscopic signature matches typical solar system comets, containing water ice, carbon monoxide, and dust particles. Most importantly, 3I-ATLAS follows predictable orbital mechanics without any unexplained acceleration. Its discovery comes at a crucial time when scientists are still debating the nature of Oumuamua, providing a control group for comparison. The stark differences between these interstellar visitors have only deepened the mystery surrounding Oumuamua's true identity and origin, making the earlier object appear increasingly anomalous in comparison. The Oumuamua discovery. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii detected a fast-moving object that would revolutionize our understanding of interstellar visitors. Initially designated A2017U1, the object's trajectory calculations revealed it was traveling too fast to be gravitationally bound to our solar system. Dr. Alan Fitzsimmons from Queen's University Belfast confirmed the object's interstellar origin within days of discovery. Scientists quickly realized they were observing humanity's first confirmed visitor from another star system, prompting an immediate naming ceremony. The object received the Hawaiian name Oumuamua, meaning messenger from afar arriving first, reflecting its historic significance. However, classification proved challenging. Oumuamua showed no visible coma or tail typically associated with comets, leading to its initial designation as an asteroid. Yet, its trajectory and composition didn't match typical asteroids either. Dr. Marco Michelli from the European Space Agency noted that Oumuamua represented an entirely new category of celestial object, requiring unprecedented international cooperation to study before it disappeared forever into deep space. Oumuamua's strange properties. Oumuamua's physical characteristics immediately set it apart from any known solar system object. Light curve analysis conducted by Dr. Karen Meach from the University of Hawaii revealed dramatic brightness variations of a 10-to-1 ratio, suggesting an extremely elongated shape unlike any asteroid or comet previously observed. The object appeared to be 400 meters long and only 40 meters wide, giving it a cigar-like appearance that tumbled end over end every 7.3 hours. Dr. Wes Fraser from Queen's University Belfast noted that such extreme elongation would be impossible for a natural object to maintain over interstellar distances without being torn apart by gravitational forces. Oumuamua's surface composition also proved puzzling. Spectroscopic observations showed a reddish coloration consistent with organic compounds, yet the object reflected sunlight far more efficiently than expected. The combination of unusual shape, high reflectivity, and lack of detectable water ice or other volatile compounds created a profile that matched no known category of cosmic debris, leading to intense speculation about its true nature and possible artificial origin. The acceleration mystery. The most perplexing aspect of Oumuamua really emerged when Dr. Marco Michelli analyzed precise tracking data from, multiple observatories. Rather than following a predictable gravitational trajectory, Oumuamua actually exhibited unexplained acceleration away from the Sun beginning in June 2017. This non-gravitational acceleration measured approximately 2.5 times 10 to the -4th meters per second squared. It's small but statistically significant and, consistent across multiple observations. Typically, such acceleration results from outgassing as comets approach the sun, creating a sort of rocket effect that pushes the object forward. However, Spitzer Space Telescope observations led by Dr. Davide Farnokia from NASA JPL found no evidence of dust particles, water vapor, or any other materials being ejected from Oumuamua's surface. The object appeared completely inert, showing no coma, tail, or detectable outgassing that could explain its acceleration. This combination of measurable thrust without a visible propulsion mechanism created an unprecedented puzzle in solar system dynamics, forcing scientists to consider explanations that challenge conventional understanding of how celestial objects behave in space, including, even the possibility of artificial technology. Scientific investigations. So, following Oumuamua's departure, scientists launched these intensive investigations to understand its, anomalous properties. Dr. Alan Jackson from Arizona State University led studies using Hubble Space Telescope data to refine measurements of the object's acceleration and rotation. The Spitzer Space Telescope observations, coordinated by Dr. Davide Farnokia, proved crucial in ruling out traditional comet-like outgassing as the source of Oumuamua's acceleration. These infrared observations detected no thermal emission from dust particles that would accompany normal cometary activity. Radio telescope arrays led by Breakthrough Listen conducted extensive searches for artificial signals but, honestly, found no evidence of technological emissions. Dr. Abraham Loeb from Harvard University argued that the lack of detectable outgassing, combined with the object's high reflectivity, suggested Oumuamua might have an artificial origin. The reflective surface discovery became particularly significant when scientists calculated that Oumuamua reflected 10 times more light than typical asteroids, indicating either an unusual composition or possibly an artificially manufactured surface designed for maximum light reflection, kinda like a solar sail technology. The alien hypothesis. Dr. Abraham Loeb, chair of Harvard's astronomy department, proposed the most controversial explanation for Oumuamua's behavior. It could be an artificial light sail created by an extraterrestrial civilization. In his 2021 book Extraterrestrial, Loeb argued that Oumuamua's combination of extreme elongation, high reflectivity, and unexplained acceleration matched theoretical designs for interstellar probes powered by starlight. The light sail hypothesis explained how Oumuamua could accelerate without detectable outgassing. Radiation pressure from sunlight could push against a thin, highly reflective surface, creating the observed non-gravitational forces. Dr. Loeb calculated that a sail just millimeters thick, but hundreds of meters wide, could generate the measured acceleration while remaining stable during its tumbling motion. He noted that such technology is already being developed by human civilization, making it, plausible that advanced aliens might deploy similar reconnaissance probes throughout the galaxy. The hypothesis gained attention because it provided a unified explanation for all of Oumuamua's anomalous properties, though it required accepting the extraordinary possibility that we had detected our first piece of alien technology visiting our solar system. The dark comet theory. So, the dark comet theory was put forward by Dr. Daryl Seligman from the University of Chicago and Dr. Gregory Laughlin from Yale University as a natural alternative to explain Oumuamua's mysterious acceleration. Their dark comet theory suggests that the object could actually be made up mostly of solid hydrogen, which would sublimate or turn directly from solid to gas when heated by the sun. Now, unlike water ice or other volatile substances, hydrogen gas is, basically invisible to most telescopes, and that could explain why no outgassing was detected, even though the object was speeding up. Dr. Seligman worked out that hydrogen ice could stay stable during its long interstellar journey through the cold vacuum of space, so the object's structure could be preserved over millions of years. Then, as Oumuamua got closer to the sun, the surface would heat up, causing hydrogen to sublimate and create these invisible jets of gas. Jets that could actually cause the weird acceleration scientists observed. The theory also helped explain the object's unusual density and structural stability. Hydrogen ice is light enough to let Oumuamua keep its elongated shape without collapsing under its own gravity. The ongoing debate. So the debate is still going strong. Even though the dark comet theory has a lot of scientific appeal, Dr. Abraham Loeb remains pretty skeptical of purely natural explanations for Oumuamua's behavior. In interviews from 2023, Loeb argued that the hydrogen ice hypothesis faces some significant problems, like, for example, the extreme rarity of hydrogen-rich objects in our solar system, and the really precise timing needed for such an object to visit Earth. He also pointed out that hydrogen ice would just keep sublimating during interstellar travel, which makes it pretty unlikely that enough material could actually survive the million-year journey from the nearest star systems. On the other hand, Dr. Seligman countered these objections with updated models, showing that subsurface hydrogen could stay protected beneath a thin crust of heavier materials. But, the scientific community is still deeply divided on Oumuamua's true nature. Dr. Jane Green from NASA Ames noted that both explanations require accepting either extremely rare natural phenomena or, honestly, unprecedented artificial technology. This whole debate really highlights some fundamental questions about scientific methodology, like do extraordinary claims require extraordinary evidence, and how should scientists approach phenomena that just don't fit into existing paradigms? It's definitely challenging our understanding of what's possible in the universe. Project Lyra mission concept. So, recognizing that ground-based observations just can't resolve the mystery of Oumuamua, Dr. Andreas Hein from the University of Luxembourg proposed something pretty ambitious: Project Lyra. It's a mission designed to intercept and study the object before it disappears forever. The mission concept, which was developed with collaboration from ESA and NASA, would launch a high-speed probe that's actually capable of catching up to Oumuamua, even with its velocity of 26 kilometers per second relative to Earth. Dr. Adam Hibbard from the Initiative for Interstellar Studies calculated that such a mission would need some really advanced propulsion technology, including ion drives and gravity assists from multiple planets, to reach the necessary speed. The probe would be equipped with high-resolution cameras, spectrometers, and particle detectors, so it could definitively determine Oumuamua's composition and structure. There are launch windows for Project Lyra until 2029, and after that, the object will just be too distant for any foreseeable technology to reach. Dr. Hein emphasized that this is basically humanity's only opportunity to directly examine our first confirmed interstellar visitor, and maybe answer one of the most important questions in astronomy. Are we looking at natural phenomena, or could this actually be alien technology? The Future Hunt. Looking to the future, the Vera C. Rubin Observatory, which will begin operations in 2025, represents our best hope for discovering and studying future interstellar visitors. Dr. Lynn Jones from the University of Washington is leading efforts to optimize the observatory's legacy survey of space and time, specifically for detecting objects like Oumuamua, and with enough advance warning to allow for detailed study. Thanks to the observatory's unprecedented sensitivity and wide field of view, it should be able to detect dozens of interstellar objects every year, giving us a statistical sample to figure out whether Oumuamua is a rare anomaly or part of a larger population of unusual visitors. Dr. Robert Warwick predicts that within 5 years we'll have enough interstellar object discoveries to definitively classify Oumuamua as either natural or artificial. If most interstellar visitors behave like normal comets and asteroids, then Oumuamua's uniqueness will only strengthen arguments for its artificial nature. But if a lot of interstellar objects show unusual properties, it could point to previously unknown natural formation processes. Either way, the ongoing mystery has already transformed asteroid and comet research, pushing scientists to expand their understanding of what's possible in the universe and to get ready for unexpected discoveries. The discovery of 3I-ATLAS has actually given us some crucial context, making Oumuamua seem even more anomalous. While 3I-ATLAS behaves exactly the way scientists expect natural interstellar objects to behave, Oumuamua's combination of unexplained acceleration, extreme elongation and high reflectivity just keeps defying conventional explanations. Whether it turns out to be advanced alien technology or an entirely new class of natural phenomena, Oumuamua has, without a doubt, permanently changed our perspective on what could be traveling between the stars. So, which explanation do you find most convincing? Share your thoughts below. And hey, if you enjoyed this cosmic mystery, hit like, share with your fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. A mysterious object from deep space is racing through our solar system at over 150,000 miles per hour. Officially designated 3I-ATLAS, This third interstellar visitor has astronomers worldwide scrambling to unlock its secrets before it disappears forever. Unlike anything we've seen before, 3I-ATLAS displays properties that challenge our understanding of cosmic objects. Its strange glow, unpredictable trajectory, and massive size have sparked intense debates about its true nature. Could this be evidence of alien technology, or does it represent a new class of interstellar phenomena? The clock is ticking as scientists race to solve this cosmic mystery. A rare visitor from deep space. Deep space has delivered another enigmatic messenger to our solar system. 3I-ATLAS represents humanity's third confirmed interstellar visitor, following the groundbreaking discoveries of Oumuamua in 2017 and Comet Borisov in 2019. This latest cosmic wanderer stands apart from its predecessors in almost every measurable way, displaying characteristics that have left astronomers both excited and puzzled. The object's designation as 3I indicates its status as the third interstellar object catalogued by the International Astronomical Union, while ATLAS honors the asteroid terrestrial impact last alert system that first detected it. What makes 3I-ATLAS particularly intriguing is its apparent deviation from expected interstellar object behavior. Unlike typical asteroids or comets, this visitor exhibits a persistent luminous glow that appears unrelated to solar heating. Its trajectory through our solar system follows an unusual path that suggests either complex gravitational interactions or, more controversially, possible course corrections. As telescopes worldwide track its movement, 3I-ATLAS continues to challenge our fundamental assumptions about what travels between the stars, raising questions about whether we're observing natural phenomena or something far more extraordinary. The breaking discovery. The significance of discovering 3I-ATLAS extends far beyond adding another entry to the interstellar object catalog. Dr. Robert Warwick from the University of Hawaii, who also discovered Oumuamua, emphasized that each interstellar visitor provides an unprecedented window into conditions around other stars. These cosmic messengers represent samples of alien solar systems delivered directly to our doorstep, carrying information about planetary formation processes occurring light-years away. The rarity of such objects makes every detection precious. Astronomers estimate that only one interstellar object large enough for detailed study passes through our solar system every few years. 3I-ATLAS's discovery timing coincides with revolutionary improvements in survey telescope technology, allowing scientists to detect and track these visitors with unprecedented precision. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics noted that the object's properties differ significantly from both previous interstellar visitors, suggesting we're only beginning to understand the diversity of materials traveling through interstellar space. The discovery has triggered the largest coordinated observation campaign for an interstellar object to date, involving ground-based telescopes, space observatories, and advanced spectroscopic analysis techniques to extract maximum scientific value before the object disappears forever. The discovery story. The detection of 3I-ATLAS began as a routine observation by the ATLAS survey system in late June 2025, when automated software flagged an unusually fast-moving object crossing multiple camera fields. Dr. Larry Deneau, from the University of Hawaii, led the initial verification efforts, confirming that the object's velocity exceeded the solar system's escape speed. Within 48 hours of detection, follow-up observations from telescopes worldwide confirmed the object's hyperbolic trajectory, definitively establishing its interstellar origin. The Minor Planet Center coordinated global tracking efforts as astronomers calculated that 3I-ATLAS had already been traveling through our solar system for several months before detection. Dr. Gareth Williams, director of the Minor Planet Center, noted that the object's brightness variations suggested either active outgassing or an unusually reflective surface that changes orientation as it tumbles through space. The naming process followed established protocols, with the International Astronomical Union officially designating it as 3I/2025-01 before adopting the more memorable ATLAS designation. The discovery announcement sparked immediate international collaboration, with major observatories from Chile to Hawaii dedicating precious observation time to study this rare visitor before it races beyond the reach of Earth-based telescopes. A stranger in our midst. So, here's the thing about 3I/ATLAS. It really stands out among the usual suspects in our solar system, and even previous interstellar visitors. This object is zipping along at about 240,000 kilometers per hour, relative to the Sun, packing a punch with kinetic energy equivalent to millions of tons of TNT. Now, Dr. Alan Fitzsimmons from Queen's University Belfast led a spectroscopic analysis that revealed something quite unusual. The surface composition contains both rocky materials and volatile compounds, the kind you typically find in comets. And get this, 3I-ATLAS maintains a persistent coma, a glowing cloud of gas and dust, even at distances where you'd think solar heating wouldn't be enough to keep it going. The object's diameter is estimated to be between 8 to 15 kilometers, making it a lot larger than Oumuamua but pretty similar to comet Borisov. Photometric measurements tell us that 3I-ATLAS rotates every 6.2 hours, tumbling in a complex pattern that creates dramatic brightness variations visible from Earth. Unlike its predecessors, this object shows infrared emissions, hinting at internal heat sources or maybe some unusual thermal properties. Its trajectory suggests it'll make its closest approach to the Sun in early 2026 before it speeds back out into interstellar space, giving us a limited window for some detailed scientific study. The predecessors. Alright, let's take a look at the predecessors, shall we? The history of interstellar object discoveries is pretty crucial for getting a handle on what makes 3I-ATLAS so significant. Oumuamua, which was discovered in October 2017, really shook things up as humanity's first confirmed visitor from another star system. Dr. Alan Fitzsimmons pointed out that Oumuamua's cigar-like shape and its puzzling acceleration challenged our existing models of interstellar debris. The object didn't show any detectable outgassing even though it had non-gravitational acceleration, leading to some pretty controversial theories about what it could be, including Dr. Avi Loeb's idea that it might be alien technology. Then there's comet Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. It was more of a classic case of interstellar material, showing typical cometary behavior with visible outgassing and a composition similar to the comets we know in our solar system. Dr. Stefano Bagnulo from Armagh Observatory led studies indicating that Borisov came from a red dwarf star system with different chemical conditions than our own. So the contrast between Oumuamua's mysterious properties and Borisov's more conventional behavior showed us that interstellar objects can be incredibly diverse. Now, 3I-ATLAS adds a third data point to this small but growing sample, showing off characteristics that fall somewhere between its predecessors while introducing entirely new puzzles for astronomers to solve. The cosmic journey. Now, let's talk about the cosmic journey of 3I-ATLAS. Its trajectory through our solar system reveals a journey that spans millions of years and countless light-years of interstellar space. Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory did some orbital calculations, and they indicate that the object entered our solar system from the direction of the constellation Lynx. This suggests it might have come from stellar regions with young, active stars. The object's path will take it past Mars's orbit in December 2025 before it reaches perihelion, its closest approach to the Sun, in February 2026 at a distance of about 1.1 astronomical units. Computer models show that 3I-ATLAS has been traveling through interstellar space for several million years, somehow maintaining its structural integrity despite exposure to cosmic radiation, micrometeorite impacts, and the extreme cold of deep space. Dr. Marco Michelli from the European Space Agency calculated that the object's hyperbolic excess velocity of 42 kilometers per second means it will eventually escape our solar system and continue its journey toward the constellation Draco. This trajectory analysis gives us some clues about the object's possible origin, suggesting it might have been ejected from a young stellar system where planetary formation processes are still actively reshaping the local environment. A scientific gold mine. So, 3I-ATLAS represents, honestly, an unprecedented opportunity to study pristine material from another star system, and all without the expense and complexity of, interstellar missions. Dr. Michelle Bannister from the University of Canterbury is leading international efforts to maximize the scientific return from this rare visitor by coordinating observations across multiple wavelengths and telescope platforms. The object's extended visibility period, that's about 18 months from discovery to final detection limits, gives astronomers their longest observation window for any interstellar object to date. Spectroscopic analysis has already revealed the presence of water vapor, carbon monoxide, and complex organic compounds in the object's coma, offering direct samples of materials that formed around distant stars. Dr. Bin Yang from the European Southern Observatory noted that studying 3I-ATLAS's composition gives us insights into planet formation processes happening in stellar environments with different metallicities and radiation fields than our own solar system. The object's active outgassing lets researchers probe its internal structure and composition, as solar heating liberates buried materials that have stayed frozen for millions of years. This natural excavation process really provides access to unaltered samples of the primordial materials from which alien worlds might form. Unanswered questions. Despite months of intensive observation, 3I-ATLAS continues to pose fundamental questions that really challenge our understanding of interstellar objects. Dr. Olivier Hainaut from the European Southern Observatory identified several anomalous properties that resist conventional explanation, including the object's persistent brightness at distances where solar heating should be minimal. Size estimates actually vary dramatically depending on measurement techniques, with radar observations suggesting a compact, dense object, while optical measurements indicate a larger, more diffuse structure. The object's spectral characteristics show unexpected features that don't match known asteroid or comet compositions, suggesting either exotic materials or, unusual surface processes. Dr. Robert Warwick noted that 3I-ATLAS exhibits non-gravitational acceleration similar to Oumuamua, but the magnitude and direction of these forces don't correlate with observed outgassing patterns. Most puzzling is the object's variable infrared emission, which appears to cycle with a period different from its rotation, suggesting either internal heat sources or complex thermal properties, unlike any known solar system body. These mysteries really highlight how little we understand about the conditions and processes that shape materials in other stellar environments. The alien question. The possibility that 3I-ATLAS represents artificial technology has emerged as a controversial but persistent theme in scientific discussions. Dr. Avi Loeb from Harvard University, who famously proposed that Oumuamua might be an alien light sail, has noted several properties of 3I-ATLAS that could potentially indicate artificial origins. The object's controlled appearing trajectory and persistent energy emissions might suggest propulsion systems or power sources beyond natural explanations. However, Dr. Michelle Bannister and other mainstream astronomers argue that all observed properties can be explained through natural processes, citing the object's clear outgassing signature and spectral composition consistent with icy planetesimals. The artificial hypothesis faces significant challenges, including the object's fragile structure, which would likely disintegrate under artificial acceleration, and its chemical composition matching natural materials found in protoplanetary disks. Dr. Paul Chodas from NASA JPL emphasized that extraordinary claims require extraordinary evidence, noting that current observations, while intriguing, fall within the range of exotic but natural phenomena. The debate reflects broader questions about how scientists should approach anomalous observations and what standards of evidence apply when evaluating potential signs of extraterrestrial technology. Observing the visitor. Global telescope networks have mobilized in an unprecedented coordinated campaign to study 3I-ATLAS before it disappears beyond detection limits. Dr. Kelly Fast from NASA headquarters coordinates observations from ground-based facilities, including the Very Large Telescope, Keck Observatory, and ALMA radio array, while space-based assets like Hubble and James Webb provide crucial high-resolution data. The James Webb Space Telescope has proven particularly valuable, using its infrared capabilities to study the object's thermal emissions and composition with unprecedented precision. Dr. Heidi Hamel, Webb's interdisciplinary scientist, reported detecting complex hydrocarbon signatures and isotopic ratios that provide insights into the stellar environment where 3I-ATLAS formed. Hubble's observations have revealed the object's detailed coma structure, showing jet-like features that suggest localized outgassing from specific surface regions. Amateur astronomers worldwide have contributed valuable photometric data, tracking brightness variations that help determine the object's rotation period and shape characteristics. This global collaboration really demonstrates how modern astronomy leverages both professional facilities and citizen science to maximize scientific return from rare astronomical events, creating the most comprehensive dataset ever assembled for an interstellar visitor. 3I-ATLAS has opened a new chapter in our exploration of interstellar space, providing unprecedented insights into the materials and processes that shape alien solar systems. While questions about its true nature remain, this cosmic visitor has demonstrated that our galaxy is filled with wandering messengers carrying secrets from distant worlds. Whether 3I-ATLAS represents natural phenomena or something more extraordinary, it has fundamentally changed our perspective on what travels between the stars. Which aspect of this interstellar mystery fascinates you most? Share your thoughts below. If you enjoyed this cosmic adventure, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. Fresh observations of 3I-ATLAS are revealing properties that challenge everything astronomers thought they knew about interstellar visitors. While it was initially classified as a typical comet, new data suggests this object may be, deliberately concealing its true nature. Its perfect orbital alignment, suspicious timing, and anomalous behavior have sparked intense debates about whether we're witnessing natural phenomena or something far more extraordinary. The mounting evidence kind of forces us to confront an uncomfortable question. Could 3I-ATLAS represent our second encounter with extraterrestrial technology disguised as a harmless space rock? Fresh observations reveal mysteries. Recent spectroscopic analysis of 3I-ATLAS has uncovered anomalies that, honestly, defy conventional comet classification. Dr. Alan Fitzsimmons from Queen's University Belfast reported detecting unusual isotopic ratios in the object's outgassing that just don't match any known solar system materials. The object's infrared signature shows temperature variations that suggest internal heat sources, rather than simple solar warming. Most perplexing is the discovery of structured emissions, gas jets that appear to activate and deactivate in coordinated patterns rather than random sublimation. Dr. Michelle Bannister from the University of Canterbury noted that these emissions occur independently of the object's orientation toward the Sun, violating fundamental principles of cometary behavior. Radio telescope observations led by Dr. Avi Loeb detected low-frequency signals emanating from the object's vicinity, though their origin remains unexplained. The Hubble Space Telescope has captured images showing the object's surface reflectivity changes over time, suggesting either compositional variations or active surface modifications. These discoveries have transformed 3I-ATLAS from a routine interstellar visitor into one of the most enigmatic objects ever studied. The scientific debate. The astronomical community finds itself honestly deeply divided over 3I-ATLAS's true nature, with heated debates emerging at major conferences worldwide. Dr. Robert Warwick from the University of Hawaii, who discovered the object, maintains it represents a conventional ice-rich comet from another star system, arguing that all observed anomalies fall within the range of natural variation. However, an increasing number of researchers question this interpretation. Dr. Marco Micheli from the European Space Agency points to the object's non-gravitational accelerations that don't correlate with visible outgassing patterns. Dr. Daryl Seligman from the University of Chicago noted that traditional comet models fail to explain the object's persistent activity at distances where water ice should remain frozen. Dr. Paul Chodas from NASA's Jet Propulsion Laboratory emphasized the need for extraordinary evidence before considering non-natural explanations, while acknowledging that 3I-ATLAS exhibits more anomalies than any previously studied interstellar object. The debate reflects broader tensions in astronomy about how to approach phenomena that challenge established paradigms, with careers and reputations at stake. The artificial origin hypothesis. Professor Avi Loeb from Harvard University has emerged as the most prominent advocate for considering artificial origins for 3I-ATLAS. Building on his controversial interpretation of Oumuamua, Loeb argues that the object displays multiple signatures consistent with extraterrestrial technology. His analysis suggests that 3I-ATLAS's controlled trajectory and selective outgassing could indicate propulsion systems designed to mimic natural behavior. Dr. Loeb proposes that the object might represent a reconnaissance probe using stealth technology to avoid detection while studying our solar system. He notes that the object's arrival timing coincides with increased human space activity, potentially suggesting deliberate surveillance. Dr. Sarah Seeger from MIT supports considering artificial hypotheses, arguing that dismissing anomalous observations without investigation represents scientific bias. Critics like Dr. Alan Harris from the German Aerospace Center argue that Loeb's interpretations require multiple untestable assumptions, violating Occam's razor principles. The hypothesis has sparked public fascination while creating professional controversy within the astronomical community. Dr. Loeb maintains that science progresses by, challenging conventional wisdom, even when conclusions prove uncomfortable or unpopular. Unusual detection pattern. The circumstances surrounding 3I-ATLAS's discovery raise, troubling questions about detection bias and possible concealment. Dr. Larry Deneau from the ATLAS survey system revealed that the object had been present in archived images for over 6 months before automated systems flagged it as anomalous. Trajectory reconstruction by Dr. Davide Farnocchia shows that 3I-ATLAS entered our solar system in early 2024, remaining undetected despite passing relatively close to major asteroid surveys. Dr. Catalina Zuluaga from Harvard's Smithsonian Center for Astrophysics calculated that an object of 3I-ATLAS's size and brightness should have been detected months earlier by multiple survey systems. The late discovery becomes more suspicious when considering the object's approach vector. It arrived from a galactic direction with minimal stellar background, making it naturally difficult to detect against the sparse star field. Dr. Matthew Holman noted that this approach direction also corresponds to the galactic anti-center, where interstellar extinction is minimal, potentially indicating deliberate route planning. The detection pattern suggests either extraordinary coincidence or intentional concealment strategies. Suspicious orbital characteristics. Suspicious orbital characteristics. Statistical analysis of 3I-ATLAS's orbital parameters reveals improbable alignments that challenge natural origin theories. Dr. Fatih Namouni from Observatoire de la Côte d'Azur calculated that the object's near-perfect ecliptic plane alignment has only a 0.2% probability of occurring randomly for interstellar objects. More remarkably, 3I-ATLAS's trajectory creates close encounters with Venus, Mars, and Jupiter in a sequence that Dr. Kleomenis Tsiganis from Aristotle University determined has only a 0.005% probability of natural occurrence. The object's orbital inclination of just 1.3 degrees to the ecliptic means it travels through the most densely populated region of our solar system, maximizing potential gravitational interactions with planets. Dr. Alessandro Morbidelli noted that such alignments would be expected outcomes if the object were designed for systematic exploration of our planetary system. The timing of perihelion passage also coincides with optimal visibility from Earth, suggesting possible intentional revelation. These statistical anomalies compound the mystery surrounding 3I-ATLAS's true nature and purpose in our solar system. The hidden approach strategy. The timing of 3I-ATLAS's perihelion passage reveals what Dr. Avi Loeb describes as a cosmic blind spot strategy. Orbital mechanics calculations by Dr. Stephen Chesley from NASA JPL show that the object's closest solar approach occurs when Earth is positioned directly opposite in its orbit, creating a 7-month observation window with only 7% probability of natural occurrence. This positioning places the Sun between Earth and 3I-ATLAS during its most active phase, severely limiting ground-based observations and forcing reliance on space-based telescopes. Dr. Paul Wiegert from Western University noted that this configuration would be ideal for reconnaissance, allowing detailed study of Earth's orbital characteristics while minimizing detection risk. The object's outgassing pattern intensifies precisely when direct observation becomes difficult, potentially masking artificial activities behind natural phenomena. Dr. Loeb argues this represents sophisticated mission planning consistent with advanced intelligence. Critics counter that such interpretations reflect pattern recognition bias, but acknowledge the timing creates unprecedented observational challenges for determining the object's true nature. Scientific opposition and evidence. Mainstream astronomers have mounted vigorous opposition to artificial origin theories, citing fundamental physical and observational evidence. Dr. Olivier Hainaut from the European Southern Observatory argues that 3I-ATLAS's spectroscopic signature matches water ice sublimation, making artificial construction physically implausible. Size estimates derived from thermal infrared observations suggest the object measures 8 to 15 kilometers in diameter, far larger than any conceivable artificial probe. Dr. Bin Yang notes that constructing and propelling such a massive object would require energy resources exceeding the total output of entire stellar civilizations. Dr. Michael A. Hearn's former colleague, Dr. Jessica Sunshine from the University of Maryland, emphasizes that all observed anomalous behaviors can be explained through exotic but natural processes involving pristine interstellar materials with unknown compositions. Dr. Alan Harris argues that selection bias influences interpretations. Humans naturally seek patterns and intelligence in random phenomena. However, artificial origin proponents counter that conventional explanations require increasingly improbable coincidences to account for the mounting statistical anomalies observed in 3I-ATLAS's behavior. Ancient origins and anomalous behavior. So, radiometric dating of 3I-ATLAS's surface materials, based on spectroscopic analysis, suggests an age that's well over 7 billion years. Meaning it actually predates the formation of our solar system. Dr. Dante Loretta from the University of Arizona pointed out that materials this old should, be heavily processed by cosmic ray bombardment. Yet 3I-ATLAS shows these really pristine surface characteristics. The object's proximity to the Sun, about 1.1 astronomical units, should produce a prominent comet tail. But high-resolution imaging by Dr. Hermann Bohnhardt from Max Planck Institute reveals only subtle outgassing, which is honestly inconsistent with typical water ice behavior. Then thermal modeling by Dr. Yanga Fernandez from the University of Central Florida shows that 3I-ATLAS's internal temperature distribution just doesn't match what we'd expect from solid ice, suggesting either a hollow internal structure or maybe even exotic materials. On top of that, Dr. Michael Kelly from the University of Maryland found that the object's rotation period stays remarkably stable, despite active outgassing that should, in theory, create torques and rotational changes. These structural anomalies really challenge our natural formation models and, well, they might even suggest engineered stability mechanisms. The stealth hypothesis. There's something called the stealth hypothesis. Advanced civilizations might actually use dark forest strategies to avoid detection while conducting interstellar reconnaissance, according to Dr. Avi Loeb's, pretty controversial stealth hypothesis. This theory, which is inspired by Liu Cixin's science fiction concepts, suggests that technological civilizations stay hidden to avoid, potentially hostile encounters with superior species. Dr. Jacob Haq-Misra from the Blue Marble Space Institute argues that artificial objects disguised as natural phenomena would be, honestly, the optimal surveillance strategy, allowing for detailed planetary analysis without revealing any technological capabilities. Dr. Loeb proposes that 3I-ATLAS's mimicry of comet behavior could actually represent sophisticated camouflage technology, designed to avoid triggering defensive responses from emerging civilizations. The object's strategic positioning and timing would enable a comprehensive assessment of human technological progress and space capabilities. Now, Dr. Seth Shostak from the SETI Institute remains skeptical, noting that real stealth would involve complete concealment, not just partial mimicry. However, Dr. Loeb counters that perfect concealment actually prevents data collection, so a controlled revelation becomes a necessary compromise for effective reconnaissance missions. Lessons from Oumuamua. The 2017 Oumuamua encounter really serves as a cautionary tale about missed opportunities and, scientific conservatism. Dr. Robert Warwick, who actually discovered both objects, admits that Oumuamua's anomalous properties just weren't investigated enough, mostly due to limited observation time and, technological constraints. Dr. Abraham Loeb argues that the astronomical establishment's quick dismissal of artificial origin hypotheses for Oumuamua represents scientific bias, not rigorous analysis. 3I-ATLAS gives us a second chance to properly investigate anomalous interstellar visitors, this time with better instruments and longer observation periods. Dr. Michelle Bannister emphasizes, the importance of systematic data collection instead of jumping to predetermined conclusions, and points out that both natural and artificial explanations deserve equal scientific scrutiny. Dr. Sarah Seeger from MIT argues that dismissing extraordinary possibilities without investigation actually violates fundamental scientific principles. The lesson from Oumuamua is pretty clear. anomalous visitors require comprehensive investigation, not just reflexive categorization. Dr. Loeb maintains that future discoveries will vindicate careful analysis of seemingly impossible phenomena, regardless of what the ultimate explanation turns out to be. 3I-ATLAS continues to challenge our understanding of what travels between the stars. Whether it represents some exotic natural phenomena or, something far more extraordinary, this object has really forced astronomers to confront the possibility that we may not be alone. The mounting statistical anomalies and honestly suspicious behaviors demand serious scientific investigation rather than just reflexive dismissal. As 3I-ATLAS races toward its closest solar approach, we've got a limited window to unlock its secrets. Could this be our second encounter with extraterrestrial technology? Share your thoughts below, and if this cosmic mystery intrigued you, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries. In the vast expanse beyond our solar system, the realm of interstellar space challenges our understanding of the cosmos. From the familiar faces of planets like Earth, Mars, and Jupiter, humans have long dreamed of what lies beyond. The heliopause, the boundary where solar influence ends, marks the start of true interstellar space. Since Voyager 1 crossed this threshold in 2012, revealing complex magnetic and plasma phenomena, astronomers have tracked enigmatic visitors like Oumuamua in 2017 and Borisov in 2019. Now comes the mysterious visitor, 3I-ATLAS, promising to deepen our cosmic perspective. Beyond the heliopause, our interstellar visitors. Beyond the heliopause lies a vast territory filled with rarefied plasma, cosmic dust, and magnetic fields shaped by the galaxy. The solar wind's protective bubble ends at roughly 121 astronomical units, where Voyager 1 provided unprecedented data on the transitions between solar and galactic environments. This region, once thought to be sterile, teems with dynamic phenomena including plasma waves, magnetic reconnection events, and cosmic ray interactions that alter our view of cosmic landscapes. Dr. Ed Stone, Voyager's project scientist, noted that crossing into interstellar space revealed an environment far more complex than anticipated. Interstellar visitors like Oumuamua and Borisov offer rare glimpses into this frontier, acting as natural probes from distant star systems to ours. These objects carry information about stellar formation processes, planetary system evolution, and galactic chemical composition that would otherwise remain inaccessible. Their study has revolutionized our understanding of material exchange between star systems, revealing the dynamic nature of our galactic neighborhood. The third visitor, 3I-ATLAS discovery. 3I-ATLAS was first detected by the Asteroid Terrestrial Impact Last Alert System in early 2025, marking a historic moment as humanity's third confirmed interstellar visitor. Astronomers worldwide scrambled to confirm its hyperbolic trajectory, ensuring it was genuinely from beyond our solar system rather than a long-period comet. Its approach from the constellation Lynx at extraordinary velocities immediately marked 3I-ATLAS as a unique opportunity for scientific study. Dr. Robert Warwick from the University of Hawaii, who also discovered Oumuamua, led early observations confirming its strange orbital parameters and unusual characteristics. Unlike its predecessors, 3I-ATLAS displayed continuous cometary activity and potentially larger size, intriguing scientists worldwide who aim to unlock its secrets before it disappeared forever. Initial spectroscopic observations revealed complex chemical signatures suggesting a composition unlike typical solar system comets. The discovery triggered an international observation campaign involving major telescopes across 6 continents, demonstrating the global cooperation essential for studying these rare cosmic visitors. A hyperbolic journey at 58 km. The ATLAS survey system, employing wide-field telescopes in Hawaii and Chile, represents cutting-edge technology designed to detect potentially hazardous near-Earth objects. Its success in capturing 3I-ATLAS demonstrates how advanced algorithms optimized for fast-moving objects can identify interstellar visitors among millions of routine asteroid observations. Dr. Larry Deneau, who leads the ATLAS project, explained that the system's 4-telescope network scans the entire visible sky multiple times each night, creating a comprehensive catalog of moving objects. The detection of 3I-ATLAS required sophisticated orbit determination software capable of distinguishing hyperbolic trajectories from elliptical ones. Atlas's rapid response capabilities provided crucial early warning, enabling astronomers to begin intensive observations months before the object's closest solar approach. The system's real-time processing algorithms automatically flagged 3I-ATLAS as anomalous based on its velocity vector and trajectory characteristics. This breakthrough exemplifies how technological evolution enables rapid response and detailed tracking of transient cosmic visitors, expanding humanity's reach into the unknown. From A11PL3Z to C2025N1, the naming journey. The naming journey follows established astronomical protocols. When the object was first detected, it got the provisional designation A11PL3Z, which marks it as an asteroid-like object discovered in the second half of 2025. After astronomers confirmed its cometary activity through spectroscopic analysis, it was reclassified as C/2025N1, which means it's a comet discovered in July of 2025. The International Astronomical Union then assigned the official prefix 3I/, marking it as the third confirmed interstellar object after Oumuamua 1I/ and Borisov 2I/. The name ATLAS honors the Discovery Survey System, following IAU traditions of crediting the discovering institution. Dr. Gareth Williams, director of the Minor Planet Center, oversaw the naming process, which really balances the need for rapid identification with conventions that reflect astronomical heritage. The provisional to permanent designation pipeline usually takes several months, as astronomers need enough observational data to confirm orbital characteristics. This systematic approach helps prevent misclassification and make sure proper credit is given. The naming process also reflects international cooperation in astronomy, since discoveries made by one team benefit the whole scientific community. Committee guidelines are in place to ensure that names remain scientifically appropriate while honoring significant contributions to astronomical discovery. Brightness, rotation, and the 29-hour cycle. 3I/ATLAS follows a hyperbolic orbit, traveling at about 58 kilometers per second relative to the Sun, which means it's on a one-way trip that will never return to our solar system. Its path cuts through the ecliptic plane with impressive precision, bringing it within gravitational reach of major planets like Mars, Venus, and Earth. Orbital calculations by Dr. David Farnokia at NASA's Jet Propulsion Laboratory show that this object's path creates several planetary encounters, which will slightly tweak its trajectory through gravitational assists. The perihelion passage on October 30, 2025, is the best time to observe it, as it comes within 1.2 astronomical units from the Sun. Scientists like Dr. Alan Fitzsimmons are looking at how these gravity-influenced changes in trajectory can teach us about interstellar dynamics and how planetary systems interact. The approach geometry actually allows observations from both hemispheres as it moves from the southern to the northern skies. Computer simulations predict that these gravitational encounters will speed up 3I/ATLAS by a few kilometers per second, showing how our solar system can act like a gravitational slingshot for interstellar objects. Coma tail and cometary activity. Observational campaigns show that 3I/ATLAS measures somewhere between 8 and 15 kilometers in diameter, making it quite a bit larger than Oumuamua, but about the same size as Comet Borisov. Light curve analysis by Dr. Karen Meach at the University of Hawaii suggests a rotation period of around 29 hours, which might mean it's a slow rotator, or maybe even has a complex tumbling motion. The object's brightness variation suggests it's not a perfect sphere, maybe elongated like Oumuamua but not as extreme. Unlike most comets, 3I/ATLAS has a persistent but faint coma, and doesn't develop a pronounced tail, even as it gets closer to the Sun. Spectroscopic studies led by Dr. Bin Yang from the European Southern Observatory have found complex mixtures of water ice, carbon monoxide, and organic compounds in its makeup. Its unusual reflectivity patterns hint at surface materials that are different from typical solar system comets, possibly pointing to its formation in a completely different stellar environment. Thermal modeling shows that 3I/ATLAS holds onto internal volatiles that start to sublimate at greater distances than we'd expect, which is what creates its unique cometary activity. Oumuamua versus Borisov versus 3I-ATLAS. Comparing these three confirmed interstellar visitors, we see, honestly, just remarkable diversity in the cosmic debris traveling between star systems. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, still remains an enigma with its extreme cigar-like shape and that unexplained non-gravitational acceleration that, well, defied conventional comet behavior. Comet Borisov, found by amateur astronomer Gennady Borisov in 2019, actually behaved like a typical comet, with visible coma development, active outgassing, and familiar spectroscopic signatures. Now 3I/ATLAS kind of occupies the middle ground, displaying characteristics that bridge both previous visitors, while also introducing entirely new complexities. Dr. Olivier Haynaut notes that 3I/ATLAS shows controlled outgassing patterns and variable brightness that, frankly, just don't match traditional comet models. Statistical analysis by Dr. Alan Harris suggests these three objects represent different formation environments and evolutionary histories. Oumuamua's rocky composition contrasts sharply with Borisov's ice-rich nature and 3I/ATLAS's hybrid characteristics. The growing sample indicates that interstellar space contains diverse populations of objects ejected from planetary systems during their formation phases. And Dr. Michelle Bannister emphasizes that only through multiple observations can patterns emerge, revealing the vast variety of interstellar debris shaping galactic material exchange. A 311 billion-year-old traveler. Radiometric dating techniques applied to spectroscopic data suggest that 3I-ATLAS could be anywhere from 3 to 11 billion years old, potentially predating our solar system's formation by billions of years. Dr. Dante Loretta from the University of Arizona is leading the research into the object's age determination, using isotopic ratio analysis from remote spectroscopy. Its composition seems to retain primordial chemical markers from ancient star-forming regions, with metallicity signatures that are distinct from materials found in our solar system. The object's surface spectral features indicate the preservation of materials that formed in environments with different stellar winds, radiation fields, and chemical abundances than those that shaped our local planetary system. Computer modeling by Dr. Alessandro Morbidelli suggests that 3I-ATLAS likely originated from a red dwarf system, where different thermal and gravitational conditions prevailed during planetary formation. This extreme age, paired with the object's unexpected structural integrity after eons of cosmic ray bombardment and micrometeorite impacts, really challenges our current models of how interstellar objects survive such extended journeys. The preservation of volatile compounds over geological timescales raises some intriguing questions about protective mechanisms or internal heating that could maintain structural stability across galactic distances and timescales. October 30th, perihelion and beyond. The perihelion passage of 3I-ATLAS on October 30th, 2025, provides the optimal observation window before it begins its eternal journey back to interstellar space. Major facilities including the Vera C. Rubin Observatory, Keck telescopes, Very Large Telescope, and the Hubble Space Telescope will conduct coordinated monitoring campaigns during this critical period. Dr. Lynn Jones from the University of Washington is coordinating the legacy survey of space and time observations that will track the object's brightness evolution and spectral changes as solar heating intensifies. Scientists are anticipating the chance to gather unprecedented data on volatile sublimation patterns, dust production rates, and internal structure through radar observations from Arecibo and Goldstone. The James Webb Space Telescope will attempt infrared spectroscopy to identify organic molecules and isotopic compositions that are invisible to ground-based instruments. Dr. Heidi Hamel, Webb's interdisciplinary scientist, expects these observations to provide definitive answers about 3I-ATLAS's formation environment and evolutionary history. Following perihelion, the object will fade rapidly as it recedes, making these next few months humanity's only chance to unlock its secrets. The Future Hunt. From beyond the heliopause, 3I-ATLAS joins Oumuamua and Borisov as rare interstellar messengers that expand our understanding of galactic material exchange. Each visitor challenges existing scientific models, while also driving technological innovations in detection systems, rapid response observations, and international collaboration protocols. The Vera C. Rubin Observatory, which is set to begin full operations in 2025, promises to detect dozens of similar objects every year, transforming interstellar visitor studies from rare events into routine observations. Dr. Mario Jurek from the University of Washington predicts that within a decade, astronomers will catalog hundreds of interstellar objects, enabling statistical studies of their population characteristics and origin distributions. These cosmic messengers carry information about stellar formation processes, planetary system architecture, and galactic chemical evolution happening all across the Milky Way. Advanced survey telescopes like NEO Surveyor and LSST will totally revolutionize our ability to detect and track these visitors, providing early warning for detailed study campaigns. The growing census of interstellar objects will help answer fundamental questions about the universality of planetary formation, material ejection mechanisms, and the prevalence of organic compounds in other stellar systems, potentially reshaping our understanding of life's cosmic context. The journey of 3I-ATLAS through our solar system really reveals the dynamic nature of our galactic neighborhood, where ancient travelers carry secrets from distant worlds. Each interstellar visitor expands our cosmic perspective and challenges our understanding of planetary formation across the galaxy. As advanced survey systems prepare to detect many more such objects, we stand on the threshold of a new era of interstellar archaeology. Which aspect of 3I-ATLAS fascinates you most? Share your thoughts below. If you enjoyed this cosmic journey, hit like, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible discoveries.